Hello! In this bonus lecture, we will elaborate on some aspects of the Newton method for finding roots, some things which we sort of skimmed over in this lecture that we dedicated to the Newton method. And at the end, we will also add some bonus, a general bonus. Let's start with the topic of usefulness of Newton method. When we ask people, okay, why is it good? There are several reasons, and one possible reason is that Newton method can provide us with dedicated, specialized iterative schemes that allow us to reach certain quantities. So let me show you two examples which are actually real life useful. Here is my first question. How do you get square root of some positive number a? Well, we remember some square roots. Square root of 4 is 2, and so on. But how about square root of 13? Well, you can pull out your calculator, you punch in 13, you press the button which is marked square root, and you get the answer. But where does the calculator get this answer? And well, it actually gets it by using a numerical method. So let's develop a numerical method for finding square root of a method which will be somehow based on the Newton approach. So, first of all, we are going to denote this unknown quantity x, and I will rewrite this as an equation which does not feature square root of a because I don't know what it is after all. So x is square root of a if x squared is a, and x is positive. Now, this new equation can be written in such a way that we are actually looking for a zero of a specific function. Let's call it fx. Well, I have two choices. Let's say that I start with x squared and I subtract a. If I flip it around, it's going to do the same job for me. Okay, I'm actually looking for the root of this function, so I'm going to apply the Newton method and develop the iterative formula which corresponds to this approach. So how does it go? Xk plus 1 is xk minus. Now in the numerator, I have to put the function and I substitute xk into it. So it will be xk squared minus a. In the denominator, I am substituting xk into derivative, 2xk. Okay, let's have a look at it. Xk plus 1 is equal to... I'm going to split this fraction into 2, and in the first part, xk squared xk, 1xk cancels, and it is just xk divided by 2, subtracted from xk. So what we get is xk divided by 2. That's just easy. The second part has minus here, so it's plus, and it's a divided by 2xk. And that's the iterative formula for finding square root of a. Now, before I start showing some examples and tell you how great it is, I'm going to rewrite it in a different way. I'm going to factor out 1/2. And this is the right moment to tell you that this method is actually much older than the Newton method. This way of estimating or approximating square root was actually invented several thousand years ago, and it's called, therefore, the Babylonian method by some authors. Now, let's have a look how Babylonians, who definitely did not have very advanced mathematics, came up with such a formula. So, you have a, and you get some xk, some estimate of the square root. Now, there are essentially two interesting possibilities. One of them is that xk is too large. It's larger than square root of a. The second possibility is that xk is actually smaller than square root of a. And then there is the third possibility that you actually have equality, but we are not going to be that lucky, so I'm going to skip that third case. It's not really realistic. Okay, xk is larger than square root of a. That's the case I'm focusing on now. How much is a over xk in this case? Well, a is actually square root of a times square root of a divided by xk. And now if I'm dividing by something which is larger than the square root of a, then I'm cancelling, and then there's still a little bit left. So this fraction must be smaller than square root of a. And therefore, I can connect it like that, and I see that the square root of a is between xk on the top and a over xk as the lower estimate. So these two numbers, the guess xk and the number a over xk, they're actually bracketing my square root. Now, by a remarkable coincidence, you can now apply exactly the same reasoning. You look at this ratio, you think about it, and you find that this ratio is now larger than square root of a. So unless you really hit the square root, unless you are that lucky, the square root that you're looking for is actually bracketed by these two expressions. Their roles are different in those two different cases, but they are still bracketing the square root. And the Babylonians actually observed this and they said, okay, if I have my square root bracketed between these two guys, why don't I look in the middle, which means taking the average? And that's exactly this formula. It's the average of the upper and lower bound. So that's how Babylonians came up with this idea. And of course, we are wiser now because we have developed some high-level mathematics. So we know that if this thing converges, then it should converge really fast. Let's have a look at it. I have some experiments prepared here. So the first thing I do, I set up the precision that I expect from the answer. And the precision, which you can see on the top, is 10 to negative 20. So I expect the answer to be correct up to 20 digits, which is wonderful. Now, to get such a precision, all the calculations have to be done with even higher precision. So to be on the safe side, I set Maple to work with 40 digits precision. That's a lot. Okay, here we go. I'm actually not using any procedure. I simply programmed the formula, which you can see over here. This is actually the form of the Babylonian average. So I'm adding xk, which is the iterate, and a over xk, and then I divide by 2. And then I sort of wrap it up in a loop where I'm doing some printing stuff, and then there is a condition which stops it. We will talk about it in a second. Let's have a look how it performs. I'm going to ask for square root of 169, which is 13. Here we go. This is actually quite useful. We talked about the error in the Newton method. It's quadratic, but the formula is useful only if the error is roughly less than 1. For larger values of error, the quadratic formula does not really give me any reasonable estimate. And you can see it over here that it took a while for the integer part of our guess to become correct, to become 13. But once the integer part is set as 13, it means that the error drops below 1, and therefore the remaining part is really quick. We can see the zeros. That's the decimal digits which are correct. Now, I talked about the quadratic convergence. I talked about the number of correct digits roughly doubling at every iteration. So let's have a look at it. Here we have 2 correct digits. The next attempt, we have 4, which is doubling. Then we add 2, 4, 5 more, which is again doubling, and a little bonus. So now we have 9 digits that are correct. And we add how many? 2, 4, 6, 8. So it's almost doubling. You see it goes roughly doubling. And over here we get still more digits which are correct. And just judging from the length, it's about double of the previous precision. So this shows that really the quadratic convergence is really, really nice. In case you are wondering, how am I testing the precision of the answer if I don't know the square root? Because I'm pretending that I don't know it. Normally, I would ask for the absolute error, which is the precise value minus my approximation. But as I just outlined, I cannot really calculate it without knowing the square root. So what people do instead, they ask about residual. They ask, okay, I'm looking for some number x. What is the job of the number x? What is the purpose? And the answer is, I'm looking for a number so that if I square it, it becomes a. So this is actually a measure, this difference, of how much my number failed to do its job. And this is called residual. And we will talk about it later quite a bit more. Typically, residual is denoted RK. So I'm checking on the residual xk squared minus a. And that's the number that I'm using in my code here in the stopping condition. If the residual drops below epsilon, then my procedure stops. Sometimes you may have divergence or something really crazy. So just to be on the safe side, I also included condition that if I get more than 23 iterations, then it should stop anyway, regardless of the outcome. But it's just to be on the safe side. So for 13, it works really nice. Let's try something really huge. Let's say 1,000,000. How much is square root of 1,000,000? The answer is 1,000. Now, again, the initial guess is not going to be really great. I'm using million again. I could actually do a much better job in the initial guess, but I'm intentionally making the life difficult for this algorithm. Okay, let's fire it up. As usual, it took a while for the integer part to settle down, but once the integer part was correct, the number of correct decimal digits quickly grew, so that's the quadratic convergence. So that's a really, really very good algorithm. Just out of curiosity, I talked about square root of 13. How much is it? Let's see. Well, that was nice. 3.60555. That's really nice, assuming that it's correct. But I quite trust this algorithm. So this is a really efficient algorithm for approximating square root, and it's even more efficient if you imagine that in those old days you had to do all the calculations by hand, those divisions, additions, things like that. So quick algorithms were really in big demand, and if you do the initial approximation right, if it's not too far off like I added over here, then this algorithm is actually very nice even for calculations by hand. So that's the Babylonian algorithm for finding the square root. Let's move to the second example. When you teach a computer or a calculator to do calculations, you naturally start with the 4 algebraic operations. Now, addition, subtraction, these are simple. Multiplication is a little bit more complicated. After all, you know how to do it by hand, and therefore it takes a little bit more time. But the worst of the lot is division. And again, you know it because you learn how to do division by hand. So imagine that you have 2 numbers, and these may be decimal numbers with rather long decimal parts. And now you have to do the calculations to get the answer. This is really time-consuming. So there is a natural question. Can we find some alternative? And since we talk about numerical mathematics, we will be actually looking for an approximation of this ratio, of this answer. And when it comes to division, this is actually not really that new, because even if you take 2 integers, you may easily end up with an irrational number as the answer, and therefore it has infinite decimal expansion. So let's say when you take 1 divided by 3, and you do the calculation by hand, you get some 3's, and after you get 10 of them, 20 of them, you get fed up and you say, okay, that's enough. So division, even in a computer which does it the traditional way, division is just approximate. Okay? So we will be asking for approximate answer, but not to this one. Instead, we are going to separate the numerator, and actually this part n times is not really a problem. And we will just focus on 1 over d. Finding a reciprocal value. That's our question. Let's call it an x. We are looking for this number. Okay, what do we know about this number? Well, by definition, the reciprocal number should work like this. If you multiply it by d, you should get 1. Now, I can rewrite it by moving 1 to the left as a root finding problem, and then I could apply the Newton method, just like we did it over here. We develop an iterative procedure, and then we try to use it, and we find that we have a problem, because in this iterative procedure, in the calculation, we would have to do division by d. But the division by d is exactly what we are trying to avoid, so that's a dead end. And therefore, although this is really good, we actually prefer to look at a slightly different function. We are looking for a number x, which is a 0 point of the expression 1 over x minus d. That's another way to characterize a reciprocal number. So we will apply the Newton formula to this function, and we will see what happens. Well, xk plus 1 is equal to xk minus, and now we have to substitute xk into this formula, and divide by the derivative of this formula. So this is actually x to negative first power, and the derivative looks like that after I substitute in. And this looks interesting. I guess I can take this minus, put it here, it becomes plus. And then I take x squared and move it here, and I leave it one there. One xk will be just like that, and the other xk, which is here, will be distributed into the bracket. So it will become 1 here minus d times xk. Now notice that in this expression over here, we actually have residual. Residual asks how much is xk failing in this job. If xk is the right answer, then this number should be 0, the residual. So we are taking essentially our previous guess, and then we modify it by the residual, by the failure, which is interesting. Now, just out of curiosity, when I see something like that, as an experienced mathematician, I would immediately factor out xk, and there would be 2 here and nothing here. Okay? But it turns out that this formula is actually more numerically stable, or to be more precise, it can actually provide better precision for the approximations. There are some really fine points about the error precision and things like that. So this is actually the formula which is used, and it has a name. This is called Newton-Raphson division. Let's see. Newton. Now this Raphson guy, I think that's it. Newton-Raphson division. Let's talk about it a little bit. First of all, let me show that I don't have to worry about all possible numbers d. In fact, I can restrict my attention to d's from the range 0.1 and 1. How come? Well, I'll show you an example. Let's say that you want to divide 1 by 13. So I'm going to take the decimal dot and shift it 2 places to the left, and then it becomes a number from this range. So I have 1 over 0.13, but how do I do it? This shifting is done by essentially pulling out 100. So I can pull it like that. And now I'm going to apply, let's say, Newton-Raphson division or any other division to 1 over 0.13, and I get some answer. And there will be some answer here. And then I simply take this answer and move the decimal dot to the right by 2 places, and I get the answer. Okay? So this division by 100 and by 1000 by 10, whatever, is actually simple. I don't have to divide. I just shift decimal dot. That's very nice. Now, the trick is computers generally work in binary code. And therefore, instead of 10, 100, and so on, you can factor out 2, 4, 8, 16, and so on. So in this way, you end up with this interesting situation that you can only worry about these from the interval 0.51. And that's it. So that's a big simplification. The second interesting thing, when does this algorithm converge? Now, for the Babylonian square root finding, this actually converges for any x0. When you have a, you can start this algorithm any place you want, any positive number. Here one has to be a little bit more careful, and it's recommended that x0 is less than 1 over d, and then the convergence is guaranteed. Not quite 1. Now it is 1. And just like with the square root finding, it's actually helpful if you can get the right first estimate, something which is easy to obtain, but it's close to the actual answer. And there is a big theory about it, some calculations which are not quite, well, they are not really easy. And eventually, the recommended starting place is something like you divide by 17, and you take 48 and subtract 32d, I think. Let me check. Well, my short-term memory was correct this time. I looked it up before the lecture. Okay. So that's essentially the theory behind the Newton-Raphson division. Let's try how it performs. So, what do we have here? I'm trying to find reciprocal to 0.9, which is a number from a range, and I actually decided not to bother with optimal starting position or optimal starting iteration. I will just put in some number. I decided to put number 2 as the universal starting point. This will make this algorithm to work harder. And as usual, I didn't use any procedure. I'm simply manually writing a loop where I'm using the formula xk plus xk times, well, exactly this formula. You can see it here. So let me run it. Here we go. And after 8 iterations, which is quite good because I started with 2, not the best guess, the correct answer is 1.n1111 and so on. And by looking at the number of ones in the answer, again, you can see that the part of the result which is correct doubles, roughly doubles with every iteration. Again, that's the square convergence. Very nice. How about, well, let's say 0.6, which is a number which is close to this other end of my range. So we will see both of these, how they perform. How much is 1 divided by 0.6? It's 1.666, something like that. Well, we will see. Wow, just 5 iterations. That was really nice. And you can see how those 6s again are spreading, how they're multiplying in numbers. This is really nice. How about 0.8? Now this is something which we should figure out. 0.8 is actually 4 over 5. So it's like that, which is 1.25. 1.25 is the answer. Let's see. Well, we got there quite quickly. Yeah, so this algorithm is really, really nice. It works well. So this much for an example, for 2 examples, how the Newton method or the Newton approach can be used to actually create dedicated formulas, dedicated procedures for finding all kinds of interesting objects. By the way, before we leave, for this particular algorithm, there is actually a nice way to show, and it's really easy, that this residual is disappearing at the quadratic rate. We had a general theory that the Newton method has error disappearing at quadratic rate. But for this nice situation, we can do, on just a few lines, the same for the residual. So how much is the next residual? Rk plus 1. Well, the next residual is actually xk plus 1 times d minus 1. How much is xk plus 1 times d? Well, xk plus 1, we can see it over here. So it's xk times d plus xk times d times 1 minus xkd. And then there is minus 1. Okay. I ran out of room. Now, what I do with this? The answer is I will just multiply out like crazy. Everything multiplied out. So which way do I want to play it? That's a good question. I'm going to factor out minus, big minus. And then I get 1 from here. Then I get minus xkd, but I also get it from here. So it will be there twice. And finally, there is minus, and I factored it out, so it will be plus. And I can see xkd, so it's xkd squared. Okay, and now I look at it and I say, wait a second. I remember this formula. This is 1 minus xkd, that all squared. Really? Let's work it backwards. 1 squared fits. 2 times this, yeah, it fits. This squared, it fits. But this is nothing else but minus rk squared. Now we are really interested in the absolute value. So if you use the absolute value, the magnitude of this residual, we get that the residual disappears at a quadratic rate, which is very nice. Okay, so much for these examples. And let's pass to something more theoretical. We keep talking about the Newton method being a method of order 2, but how do we know that it's true? Perhaps we are all victims of some vast conspiracy, an evil conspiracy. Well, fortunately in mathematics, if you're in doubt, you can simply look up a proof. So let's have a look how the proof of the theorem that we have here goes. First, we start with some setup. We have a number, r, and we have a function. Now we are assuming that this number r is a root of f, which means that fr is 0. And we also assume that r is simple in the first part. Let me put it like that. Then we say that we only check it for functions which are twice continuously differentiable. So there must be some neighborhood of this r, of this root, on which the function of f has derivative of order 2, which is continuous, and also of order 1. We can write it like that. F belongs to C2 of some neighborhood of r. That's a mathematical notation. And finally, we need to check it somehow. So how does the order checking go? These are general assumptions. And now we have to look at a specific instance. We take the Newton method with some initial x0, we apply it, and we get a sequence. So xk is produced by Newton. And we assume that this sequence goes to R. Now remember, when we are checking the order of a method, we only check it on sequences that actually go to the root. Because for every method you can also generate, or for most methods, you can also generate sometimes sequences that do not go to the root, and that it doesn't really make much sense to ask how quickly they go there if they don't go there. Okay? So that's an assumption which is a part of the definition of the order of a method. We only check it on convergent sequences. And our aim is now to show that the error of these individual approximations satisfies a certain formula. So the error that we are interested in is the difference between the actual root and our approximation. And that's essentially it. That's the setup. Let's have a look at it. How much is the error for the next iteration? Well, by definition, it's the actual result, the root, minus xk plus 1. And then, of course, we can substitute for xk plus 1, and we put xk minus, and this minus gives me plus, fxk divided by f prime xk, which can be written, and now I look here, and this is just ek, plus fxk divided by f prime xk. That's very nice. Now, before we move on, I'm going to focus on what's happening with the root. If r is the root of our function, then we should be able to write the function as follows. We factor out x minus r, and then there is some function which is left, and this function again should be twice continuously differentiable on some neighborhood of our root. Moreover, if we ask that gr is not 0, then we have to put m here, and we learn about multiplicity of r as a root. Now, we will then focus on the case when r is a simple root, so m is equal to 1. But for now, let's do it in a general way. So our formula looks like this. ek plus 1 is ek plus, we have to put xk into f, which is over here, xk minus r to power m times gxk divided by, okay, how optimistic or pessimistic am I? Well, we will see. I'm differentiating this function f, which means here I have to use the product rule. First, I take derivative of the power. M times xk minus r to power m minus 1 is multiplied by gxk. So far, so good. Plus, the power is kept, xk minus r to power m, and I substitute into g prime my point xk. Yeah, I managed. Good. Okay, what else? Okay, some cancelling, some reorganization. Perhaps, let me play with it a little bit. First, this is ek plus, I'm going to cancel xk minus r to power m minus 1 in the whole fraction. Okay, and I'm going to factor out m. from the denominator, so it appears down here. When I cancel xk minus r to the power m minus 1, it disappears from here. Here there will be one left, so I just take away m. Here there will be one left. I take away m. So far so good. Then I take this xk minus r from the top and pull it out also. And I get a fraction on the top, gxk. In the denominator, m I pulled out. Well, so it's just gxk plus xk minus r, there is one left, and there is the derivative, gxk. But I shouldn't forget, I also pulled out m from the denominator. So there is 1 over m over here. Do I like it? We will see. Next move. ek. Now, xk minus r, that's almost ek. It's just the other way around in the difference. So it's actually minus ek. Minus 1 over m ek. Now, this is becoming interesting. There is a chance for cancelling, I hope. But there is this fraction. So what do? I divide in the fraction by gxk. I get 1 on the top, 1 here. Now again, xk minus r, this is actually minus ek. Then there will be g prime xk over gxk times 1 over m. Okay. So far, so good. Do I like it? I think I'm going the right way. Now, let's introduce some notation. Function hx will be 1 over m g prime x over g x. So essentially, this part over here. And therefore, I can write this as ek minus 1 over m ek 1 over 1 minus ek hx. Just to make my life xk, sorry. xk. Just to make my life easier. Now it's getting interesting. This number over here, what do I know about it? Good question. Well, first we start with xk. xk is supposed to be convergent to r. And therefore, gxk over gxk, and one of them is differentiated. Which one? The top one. So the top one has derivative, the bottom one does not. Where do I see them? Over here. This ratio, therefore, converges to g prime r over gr. Does it make sense? Well, gr is not 0. And therefore, this ratio on the right, this limit, makes sense. It's a real number. And function g is continuous, and also its derivative is continuous. And therefore, due to this continuity, we have something like that. So the sequence g prime xk over gxk is convergent. And as a convergent sequence, it must be bounded. Moreover, when I divide by m, which is over here, again, this does not change the boundedness. And from this it follows that the sequence hxk is bounded, and therefore I have an upper bound for it. That's the first important observation. The second important observation is that since xk goes to r, then the error must go to 0. What does it mean? Well, this number is bounded, and this number goes to 0. Therefore, the whole thing, this whole number goes to 0. And if I cut away some small k's, which I can do, I'm only interested in what's happening towards the end of the convergence. So if I cut away a finite number of k's, for all the remaining ones, this number becomes smaller than 1 in absolute value. Now, when I see a formula like that, 1 over 1 minus something which is small, I immediately think of a geometric series. That's actually the expression for the sum of a geometric series. So what do I have is ek minus 1 over m ek, and now this ratio gets replaced by 1 plus this factor plus this factor squared plus this factor cubed plus and so on. What do we know about these numbers? Well, it's actually one number taken to different powers, raised to different powers, and this number is going to 0 because it's a bounded expression multiplied by something that goes to 0. So sooner or later, these numbers are going to be really small, and then the higher powers will become negligible. So I'm going to cheat a little bit, but just a little bit. This is the traditional part of any, let's say, more serious proof. And I will simply ignore the higher powers. So this part is out. And let me write down what I obtain. I have ek minus 1 over m ek minus 1 over m h xk times ek squared. And that's the formula that I wanted to see. Let me do one more trick. I don't know how much this is, but this is bounded. So this coefficient here in absolute value is bounded by some capital C. Now, how does it work without cheating? Well, actually, if I didn't want to cheat, then at this stage, instead of passing to a geometric series, I would pass to a Taylor polynomial with Lagrange form of remainder. And for that, I would need a derivative of h, which means I would need the second derivative of g, which is something that I have in my assumptions. G is twice differentiable. We didn't use second derivative before. I would need it here to make these calculations precise. But in this way, it was much easier. And it gives the right message. So here is the formula that I have for the next error. Now let's go back to our assumptions. We are really interested only in simple roots. What does it mean that the root is simple? Simple means that m is equal to 1. And when m is equal to 1, then ek actually cancels. And when I pass to absolute value, I get that ek plus 1, the next error, is bounded by some constant times the previous error squared, which is what we have over here. That's the constant. And this is finally the proof that the Newton method behaves as a method of order 2 for simple roots. Now, there are actually proofs of quadratic convergence that are, let's say, a bit easier than this one. However, the way we proved it allows us to answer some interesting questions. And of course, the first question is what happens if we have a root which has multiplicity larger than 1? What can we say about the error then? Well, ek plus 1 in absolute value, and I look here, if m is not 1, then this fraction is not 1 either, and ek does not cancel. It remains in the formula. I use common denominator, I divide by m, and on the top it will be m minus 1 ek in absolute value. I'm taking absolute values. Then there is another term which features ek squared. But ek is a small number, so when I square it, it becomes negligible. So I will drop the higher power terms, and again I will use this approximating mark. So this is the formula for the error when your root is of higher multiplicity. Well, this is actually a linear behavior for the method. And that's exactly the second part of the statement. For roots of higher multiplicity, the method is of order 1. So now the whole theorem is proved. We can celebrate. Here we go. Celebratory square. And let's return to this place. Of course, we are unhappy. We are deeply unhappy that for roots of higher multiplicity, we do not have quadratic convergence. How can we fix it? Well, let's have a look here. ek would cancel if we could take this part, or perhaps this part, and multiply it by m. Can we do it? Well, then we would have to multiply by m this part, or this part, or this part, or this part, or this part. And this is actually the part of the Newton formula. So here is an interesting idea. What if I use this modification? My new Newton formula looks like this: xk minus m times fxk over f prime xk. Now for roots of multiplicity m, this should now be a quadratic method, because in these estimates there will be extra m on the top and ek cancels. This is interesting. Let's try it experimentally. I have a problem here prepared which looks like this: x times x minus 2 times x plus 2. That's a simple polynomial, and it has 3 roots, and I'm going to be interested in this 0 root. Now it's of multiplicity 1. Then I look at x squared, x minus 2x plus 2, and x cubed, x minus 2x plus 2, and so on. We can increase multiplicity easily. Now I will try to find 0 using the Newton method, always starting from the same place so that we have sort of like comparable runs. Okay? So let's have a look at the code. Let's go back to precision 10, and here I'm starting at 0.7 with tolerance 0.01, which is not really all that great, and let's start with the linear guy. So when I tried 0 as a root of multiplicity 1, I got the answer in 4 iterations. Now let's go back and put square there. And when I do that, and I start from the same x0, suddenly it takes 10 iterations to get there. So you can see the slowness, the sudden slowness of the Newton method. But I know that this is actually a root of multiplicity 2, and my procedure can handle that. I have a specific form. Instead of specifying a method to be Newton, I put Newton with 2, and this 2 is put over here in the formula. And now let's see the performance. It took 3 iterations for the special Newton version for the right multiplicity. Let's try with cube. So first I'm going to increase the multiplicity to 3 in both commands, and then I change the Newton method to variation when m is equal to 3. So let's run the original Newton method, just like that. The method is Newton for x cubed, a root of multiplicity 3, and it takes 15 iterations. And this is not unexpected. The higher the multiplicity, the worse the performance, essentially. But now let's try the special version of Newton with constant 3 in it, and it takes 3 iterations to get the root. So what's the conclusion? Well, it seems to work. Essentially, that's the conclusion. However, this brings us to another question. We know how to modify the Newton method if we know the multiplicity of the root, but where do we get this information? That's a very good question. We can see it easily from polynomials, but there are other functions. For instance, let's have a look at this one. fx is equal to 1 minus cosine x. And let's focus on the root x is equal to 0, which is a very nice root. But the question is it simple or not? Now, this is not a polynomial, so how can we tell? Of course, we know from calculus that there are procedures that can handle this question, and we can answer rather easily, and we actually know the order of this root because it's very popular. But there are situations when these tools cannot be applied. You simply have a function, perhaps it's not even given by a formula. Perhaps the values of the function are given by some experiments. And then you simply do not have any tools, any analytic tools to determine the multiplicity of your root, and then you have a problem. Can we somehow get this information from data? And the answer is yes, and the answer is hidden here in this approximation or in this estimate of the error. Let's have a look at it. So, on the left, and let me skip the absolute values, let me go back to this formula. There is the error of the next approximation, which is r minus xk plus 1. Now, this is supposed to be, and let's have a look here, I put together the fractions when I factor out ek, and I get m minus 1 over m, and here I should put ek, which is r minus xk. Now, when I'm doing the run of a Newton method, of the usual Newton method, without modification, the original one, I get xk, I get xk plus 1. That's the pieces of data that I have, but there are two unknowns. The root, which I don't know, of course, naturally, and the multiplicity. So I have one equation for two unknowns. That's not enough. So I make another iteration of the Newton method, and again I compare the errors. So this is the error for the next iteration, xk plus 2, and the formula is actually the same. I just have to shift indices by 1. So using the Newton method, I produce three successive approximations, xk, xk plus 1, xk plus 2, and they come here into these two equations, and now I have two equations with two unknowns. I should be able to first eliminate r, and second, get m. So how do I eliminate r? Well, actually, it's enough if I take the first equation and subtract the second, because r cancels. And here, when you multiply out the bracket, m minus 1 over m, r also cancels. So I can just imagine that it's not there, okay? And let's make my life a little bit easier now. Also, I take the first equation multiplied by m, and I do the same with the second equation. So you can imagine that I multiply, and there is mr, it cancels. And what I get is minus m xk plus 1, and I'm subtracting number 2, so it will be plus m xk plus 2 is equal to, and there's m minus 1r, and m minus 1r, it cancels, and then I'm subtracting m minus 1 xk, and adding, because this second equation is subtracted, m minus 1 xk plus 1. Okay. That's a formula. I'm going to put together all the parts which have, where is it? Okay, I'm putting all parts that have m in them on one side and parts without m on the other side. Now, which way will I go? Let's say that m goes to the right and everything which does not have m goes to the left, because there's just few of it. Let's see what's there without m. This guy does not have m in it when I multiply out. So it will be xk plus 1 after I move it to the left. And this guy does not have m in it, and I move it to the left, plus, plus, over here it's minus. Now let's see what numbers have m in them. I can see minus m xk, so it will be minus xk after I factor out m. That's this part. I can see plus m xk plus 1. That's this part. Then there is another m xk plus 1 with minus. I move it here, it becomes plus, and there's actually two of them. That's this part. And this part moves to the left, it becomes minus xk plus 2. Does it look familiar? I think I'm on the right track. So from here I isolate m, and I get a formula on the top, xk plus 1 minus xk, and in the denominator 2xk plus 1 minus xk plus 2. And that's the estimate for the multiplicity of the root, assuming that I do 3 iterations in a row using the Newton method. If I wanted to use a different method, I would get a different formula for the errors. Everything would be different, okay? So this is a specialized version for the Newton method. Let's try it on our polynomials. Okay, so here is the polynomial where I put x squared, so 0 is of multiplicity 2, and I use the usual Newton method, and this time I will store the output into a sequence. Here we go. So my sequence is a bunch of numbers. Actually, it's the numbers that we saw before, and there's 10 of them. 10 iterations. Yeah, that was exactly this run. Standard Newton for x squared case. Now I'm going to pick some k and a triple from this sequence. So I decided, I don't know why, I thought that taking n equal to 5 might be interesting. So I start with 5, go to 6 and 7. And I substitute into the formula. So here is my formula, and when I look at it, let's say in the denominator, I can see twice k plus 1. Yeah, I can see there, twice n plus 1 minus xn plus 2. This all fits. And the approximation of the multiplicity of this root is 2, which fits. And of course, if I go farther in the sequence of the answers, let's say if I go to 7, I expect to see better approximation of the multiplicity. Right now it's 1 and 3 nines. Let's see, 1 and 4 nines. So I used 7, 8, 9 iterations, 7 and 8, 9. I can still go one farther because I have 10 iterations, so I can go 8, 9, 10. And let's see, 1.1, 2, 3, 4 nines. And now we have 5 nines. So at this moment, I would say, yeah, probably multiplicity of this root is 2. Okay, let's try it with x cubed. So here is my run, x cubed. And this time it took 15 iterations, so I can take 13 as the starting iteration, this xk, over here, and then it will be 14, 15 for the indices. And let's see what's the approximation of the multiplicity, and it's 2.9999. Yeah, it's 3, so it seems to work. Now, let's go to our function 1 minus cosine. First, I'm going to try the usual Newton method, and to get to the answer, I needed 10 iterations, which is, well, not exactly as quick as I would expect. So it makes me suspicious that the root I'm looking for is of higher multiplicity. By the way, you might say, okay, we already have the answer with prescribed precision, so why do I want to do it again? Well, normally you look at those iterations, how they go, and after a few, if they don't seem to be going really quickly, you stop it, and you ask for the order, and you continue with the better Newton version. Okay? That's how it would go normally. So here I have some results, and let's say if I take 5, 6, and 7 iterations. Let's say that I stopped it after 7 iterations because I wasn't patient enough. So after 7 iterations, I thought, no, this is too slow. And we take iterations 5, 6, 7, 5, 6, 7. And I can see that most likely the root that we are looking for is of multiplicity 2. I can see here a very nice estimate, which is quite eloquent. So I'm going to use the Newton method. Instead of 1, I put 2 for m here, and I expect much better convergence. And it is. In just 3 iterations, I'm there. Okay? So this is very, very nice. Let me just, for comparison, write down the data. So the original run was 10, and we improved it to 3 by going to the right Newton method. Now, this all has been sort of tailored for the Newton method. But you may ask, okay, what if I want to use another method? Let's say the secant method. And there things are not that easy because if you remember, the secant method has order something like the golden ratio. So this gets interesting. Interesting is the right word. Perhaps we can develop some general trick that would allow us to deal with roots of higher multiplicity. So you have a function, you have a root, you try some method, and after a few iterations you say, okay, this seems to be really slow. Perhaps this is a root of high multiplicity. Can I fix it somehow? Well, this will be enough. So you have a function, you have a root. Multiplicity. Any multiplicity. 1, 2, whatever you want. But let's imagine that it's larger than 1. When you have a function and a root with higher multiplicity, you can recognize it from this form. We had it here on the blackboard without xk, so just ignore k. Now just read x. Gx, x minus r to power m. That's how you can see the multiplicity of the root. Now, here we did something interesting. We took the function and we divided by the derivative. And when we did, then the factor which is actually creating the root cancelled, almost. It disappeared, the powers disappeared, and now it is here only once. And r cannot be root here because gr is not 0. That's how we set it up. So from original multiplicity m, we are suddenly here at multiplicity 1. And that's a general rule. When you take auxiliary function fx over f prime x, then r is a simple root. So whenever you have suspicion about high multiplicity, you can try this trick. Downside is that you need to know derivative. So if you are in a situation when you don't have the derivative, and we talked about it before that this actually happens in applications quite a bit, then this trick is not for you. But let's see that it works. So here I'm applying ordinary Newton method to function 1 minus cosine f divided by its derivative. So I'm exactly looking at this case, 1 minus cosine x, trying the new general trick. Let's see how many iterations it will take. Here we go, 3 iterations. So the trick with f divided by f prime leads to 3 iterations. So it really seems to work. And it does. Theoretically, this is a very neat idea, which is why I have shown it to you. However, from practical point of view, the fact that you have to work with such a complicated formula, this requires some extra work. It's not exactly pleasant, so people try to avoid it if possible. Moreover, in many situations, and we have been talking about it, you actually do not have the derivative available. So theoretically, this is neat, but it's not as practical as it would seem. And that's it for today. So in the next lecture, I will show you some interesting ideas how to speed up the methods that we already have. And I will also show you some state-of-the-art methods for finding roots. And we will do a general comparison on different examples. So you can compare their performance. So I think you will enjoy it. See you there. So I think you will enjoy it. See you there. Yes.